You've seen in the previous section that it is possible for two or more threads to share data, but it takes a little work to make everything function reliably. To start, you need a locked shared variable that both threads can access. Any reads and writes have to be protected with a critical section, because otherwise both threads might read and write the variable at the same time, and there is the risk of a race condition. But that's not all. You also need two auto reset events to synchronize the threads. When the thread that is providing data has actual data available, it first needs to send a signal to the receiving thread that it is ready to send data. You can easily implement this with the wait1 method of an auto reset event variable. The providing thread then suspends itself, waiting for an answer. The other thread, the one that's waiting for the data, eventually reaches a point in code where it needs the data. The first thing it does is signal to the providing thread that it is ready to receive by calling set on the same auto reset event. So now the providing thread wakes up, knowing that the receiving thread is ready to receive data. But we're not done yet. To make sure that the receiving thread reads from the shared variable only after the providing thread has written into it, we need another auto reset event. Now the receiving thread signals that it is waiting for the data by calling wait1 on the second auto reset event. The receiving thread then suspends itself, waiting for the data to become available. In the meantime, the providing thread has already started writing to the shared variable. When it finishes, it calls the set method on the second auto reset event to signal to the receiving thread that the shared variable has been updated and is ready to be read. The receiving thread wakes up, reads the shared variable, and retrieves the data. This design provides a very robust communication channel between two threads that need to exchange data. Now, you might be wondering, in asynchronous applications, threads are exchanging data all the time. Aren't there any pre-built classes that can help us with this code? Oddly enough, until C# version 4, there wasn't, and you had to rely on third-party tools. But in version 4, Microsoft released the Task Parallel Library, or TPL, and it is packed with features that make writing asynchronous code a lot easier. In this section, I am going to take a closer look at the Task class, the workhorse of asynchronous programming in C#. So how would you make two threads exchange data with the Task class? Let's take a look. I've written a simple program that uses tasks to calculate data asynchronously. You can see up here that I have no field declarations whatsoever. There's no need for auto reset events or synchronization variables for critical sections. The task will do all of that internally. Here is the main program loop, Let's go through it line by line. The first thing that happens here is that I create a new task by calling task.factory.startNew. This will create a new task and immediately start it in the background. You can see that task is a generic class with a string type argument. Now, this string type is the type of data that the task will return. The startNew method expects a single argument, which is a function delegate that must return a string value. You can see here that my delegate is very simple. It sleeps for 2 seconds and then returns mark. So, the main program starts and runs this new task, and then immediately continues down here. It writes "your name is" on the console, and then accesses the result of the task. Now, notice that there is no synchronization logic anywhere. No auto reset events, no calls to set or wait one. I simply create a new task and have it return my first name. And down here I retrieve the task result and display it on the console without waiting if the task is finished or not. You might be wondering, how reliable is this code? What happens when the main program asks for the result before the task is ready? The result value will probably be null, and we would get a null reference exception in the console write method. Well, okay, let's find out. I'm going to run the program now. And there's our answer. The main program thread actually waits 2 seconds until the result is available and then displays the first name on the console. So there is some kind of waiting logic built right into the result property. And I can actually show you that code. If I set a breakpoint on the final line of the program and then start the debugger, then I can request to view the definition of the result property. And here it is. You can see that the result property first checks if the task result is available. If it is not, it calls wait, which will block until the task is ready. The code then checks if an exception has occurred, and if everything is okay, it returns the task result here. You can also see here that the set method of the property is internal. This means that only the task itself can write to the result field, and therefore there is no need for a lock statement and a critical section, because two separate threads can never read and write the result at the same time. You can see that the task class is a huge improvement when writing asynchronous code. We no longer have to worry about thread synchronization and shared variable locking. All you need to do is define the work to be done in a lambda expression, create and start the task, and then access the results whenever you need it. The result property automatically blocks until the data is available. So, when should you use tasks? Well, anytime when you have discrete units of work that can be executed asynchronously and that may or may not return a result to the calling thread. Tasks are lightweight abstractions around a single unit of work, and you can create as many as you like. Hundreds or thousands of tasks are no problem at all. Even millions of tasks is possible if you are careful. So, to summarize, the Task Parallel library provides a very handy task class for asynchronously performing a unit of work and returning the result to another thread. You access the result property when you need the result of the task. The property automatically blocks if a result is not yet available. Tasks are lightweight abstractions of an asynchronous unit of work, and you can safely create hundreds or thousands of tasks.